Let's get to it. So, let me actually start with Mathematica today. Or actually, you know what? Nope, there's one other thing I needed to do on paper first. Okay, so last time I defined the gradient, right? It was just the two partial derivatives put together into a vector. And if you had a function of like 3 or 4 or 5 variables, then it would just be all of the partial derivatives put each one in one of the coordinates, and okay, whatever. The last thing I didn't quite get to last time was, well, let's think back to Calc 1. Right? In Calc 1, we could talk about second derivatives. Well, what is the second derivative? It's the derivative of the derivative, right? Okay, great. But if we're doing partial derivatives, there are actually 4 different second derivatives for a two-variable function. So if we have a function f of xy, then we can take the derivative with respect to x or the derivative with respect to y, and we get 2 different things. Okay? Well, each of those things might depend still on x and y, so I can take the derivative of each of them with respect to x or with respect to y, and so what I get is sort of a family tree here. Okay, of taking the derivative with respect to one thing and then the other, or I could do it with respect to x each time, or I could do it with respect to y both times. Okay, so first off, does the notation make sense? Right, this looks like the notation for second derivatives from Calc 1, except we're using the little weird looking shape instead of a D. Okay, here's where it's a little different from Calc 1 because there's these 2 dudes in the middle, right? So this is something that we didn't have in Calc 1 because I could have taken the derivative with respect to x first and then y. That's the one in red. Or I could have done y first and then x. That's the one in blue. Okay. Now, what do you guys think? What does your spidey sense tell you about red and blue? Okay, there's that, right? Why does it seem like they're out of order? Well, first off, it's because, so let me just write the red one here. Okay, that's the order that we mean. So the thing on the right actually goes first. Okay, and that kind of note. Think about like function composition, right? If you write f of g of x, which function evaluated first? G, not f, even though you wrote them in the other order, right? So that yes, the order matters. Okay, and let me do the same thing for the blue one while we're at it, just for completeness. Okay, so but I've got good news for you. What do you think is true about the red and the blue ones? They kind of look very similar, right? It turns out that if the function f is nice, and there is a technical definition for nice, but um, then they turn out that they are the same thing. That's not true for all functions, but it is true if f is, quote, nice. And basically all the functions we'll deal with are nice. So
what's the actual word?
It's a little more complicated. But whatever. Okay. So yeah, so in practice, it doesn't actually matter which way you do it. What that means, though, is that sometimes it's really easy to do it in one order, but kind of a pain in the butt to do it in the other. So, if you've got the choice and you know that they're going to come out the same in the end, then might as well pick the easier order, whatever that appears to be. Well, you'd have to know what the function is, right? You'd have to look at the function and say, oh, if I take the derivative with respect to x first, all this crap cancels. But if I do it with respect to y first, then that doesn't happen.
But they're like being multiplied.
No, they're not. It looks like it's multiplied, right? But it's really function composition. Right, because what does this mean? It means take the derivative with respect to x, and then take the derivative with respect to y. Okay, so like right here, that's not multiplication. That's really function composition. Okay, or in this case, what I should be more clear, I should say functional composition. And the distinction is that, so what's a function? You put in a number, it spits out a number. Or you put in a couple of numbers, it spits out a number, or something like that, right? So what's a functional? Well, the derivative is an example of one of these. What do you give the derivative? Not a number, but an entire function, right? So you say, okay, derivative, I'm going to give you x squared, and what does it return? A different function, right? So it's like a function that acts on other functions. Okay, so we call these things operators or functionals or whatever, right? So, yeah. Okay, so I forgot to mention that last time. And what do you think the physical interpretation of these things are going to be? Well, what was the interpretation of the second derivative in Calc 1? So, like, in terms of drawing graphs, right, if I drew something like that, okay, what does the first derivative tell me? It tells me that I've hit a peak here and a valley here, right, that I've got critical points there and there. But how do I know which one's the peak and which one's the valley? I mean, other than the picture.
The first one is going up and down.
Okay, yeah, that's one way to do it, right? Is you look at the first derivative, you say, oh, the first derivative is positive, then negative. That means I went through a maximum. Okay. What's the other way to do it? Well, what's the second derivative? Yeah, it's the concavity. And here, it's concave down in the first case and concave up in the second. And where is the changeover? It's somewhere there at an inflection point, right? So the second derivative, we've got a bit of a problem. In Calc 1, there's only one second derivative, and it could be plus or it could be minus or zero. Now we have 4 second derivatives. So how the hell are we going to go from that to understanding this notion of concavity? Okay, so essentially, these 4 partial derivatives, are really 3, right? Because 2 of them are equal to each other, are going to have something to do with a generalized idea of concavity at a point. And what we'll have to figure out, and we'll have to come back to this a different day, is how to interpret that. So basically, how do we do maxes and mins and that sort of optimization stuff in a multivariable context? And it turns out it's a lot more complicated than single variable calculus, but it's not too bad. Okay. Okay, so that's the first thing I wanted to mention. The second, let me go over to Mathematica. And let me make sure the stream is set for Mathematica and make sure that it actually went over. Doesn't look like it. There we go. Okay, so let me just graph a random function. Okay, and I'm going to make this the world's stupidest function. Okay, wow, it's a plane. How exciting. Okay, all right. Oh, yeah. I was like, why are you making sound effects? Yeah.
Okay.
Huh?
Mic check.
Yeah, it's definitely a Monday. Um, okay, so great. What's the volume underneath that plane? No. Well, okay. Yeah, between the XY plane and this plane, right? So the underneath the plane is sort of that white space, right? What's the volume of that? And yes, Cole, it's one. How did Cole get one?
He's built different.
Huh?
What?
Because he's built different? Oh, you're built different, all right. Right, because it's a box, right? It's a box with length one, with height one, with depth one. Okay, so big shock, the volume is one. But not every surface is this nice, right? What about if your jerk professor comes along and does something like this? What's the volume underneath this guy? Well, who knows, right? Okay, so in the case when it was a box, it was really bloody obvious, right? You just did it, right? But we're in a calculus class, and so if I want to talk about volume or area, what is this code for? Yeah, we got to learn how to do integrals in a multivariable context. Huh? That's what you were leaning toward? Mm-hmm. Is integrals?
Yeah,
Yeah, well, you get awake and then you get the coffee, and that makes you more awake, right? Because all coffee does is lets you do stupid things faster with more energy.
yeah. That's me in ice water.
Really?
You just condense yourself that ice water wakes up and gives energy, and then it does.
Okay, then. It was their last final command.
Is that a reference? Wait, was that a reference?
Yeah, to 1984.
The book?
Yes.
I read that.
Yeah.
No.
Yeah. All right. Okay. So anyway, we need to figure out how to do an integral in a multivariable context. Okay. Now, if we think about this in the case of this weird shape that I've made, okay, what we can do is, so let's sort of think about this almost in the same way that we did when we were doing work, okay? When we were doing a work problem, we took sort of a slice of the thing and we figured out what the weight of that slice was in terms of the material that made it up. And then we also had to worry about the distance that had to get moved. But what we basically did was we had a two-dimensional slice and then we integrated over all two-dimensional slices. Yeah? Okay. Here, though, what's different, and like with work, the shape of the two-dimensional slice changed. Okay, so for example, let's take my shape here. Let me go over to a new page and let me go back to the Elgato. Um, okay, so here, um, let's say if y equals 0, my shape and x was whatever, it looked like this. Okay, and we had a function here, f of, well, it'd be f of x comma 0. Okay, and if I said, okay, take this at y equals some random value y, then the curve might look different. Okay, so I know it sounds stupid to say if y equals y. Um, let me think of it as y is a variable. Well, okay, let me just not be stupid and just this properly. Let me think of it y being at the moment taking on some constant value y naught. Then what's the area underneath this thing? Well, it'd be the integral from a to b of f of x y naught dx. Yeah? Okay, so f of x comma y naught would be a formula of some sort that involves the variable x and the number y naught. Yes? Okay, and then the x value ranges from some number to some number, so let's just call that a to b. Okay, good. So if that is the area of one of these slices, and I want to total up the area of all of the slices, well, then what do I need to do? Okay, so let me say it this way. Area of one slice um, okay, so now here's where I'm going to make the change, and instead of saying y naught, I'm just going to think about it as y, right? That y is a variable that can take on whatever range of values it can take on, okay? And but if I'm talking about um, an integral with respect to x, then anywhere I see a y, I just treat it as if it's a constant. Okay, so if the area of one slice is that, then the sum total of all slices would be just to integrate the area of all of each individual slice, but now where y is the variable. Okay, and in this case, I'm going to say, all right, y can take on the values between, say, c and d. Might not be the same number as the other one, so I'll just use something generic there. Okay, so what have we done here? We've basically done the integral of an integral. Why? Well, because what is the integral, a single integral? What can we use that to describe? Okay, but what are we trying to find here? We're trying to find volume under a surface, right? So if the area under the curve is the area of one of these slices, then the volume would be the total of all of those slices' areas. Ah, because it's not a cube, right? The depth, like how deep it is, changes based on where you are. So let me go back to the figure. Then you could do that, right? Like you did with the cube, for example. Okay, but see, like here, the distance from this edge to the surface is smaller at the top of it than it is towards the bottom of it. So there's not a constant depth that I can just multiply by. It's not so much an average, but no, that wouldn't work. Okay. Okay. So let's set up the integral for this particular surface that we're looking at. Let me switch back over here, and I'll put the figure back up. Okay. So in our case, what's our function? An x range between 0 and 1, and coincidentally, y also range between 0 and 1. And that's only because I just picked them that way in my figure. Okay. Okay, so this is the problem that we have, right? We need to integrate x squared plus y squared with respect to x. Okay, so step one, let's do the thing on the inside of the parentheses. All right, now, what is the integral of x squared? Thank you. What is the integral of y squared? Ah, with respect to x, my friend. Well, I said it now, right? Okay, but it's not y cubed over 3. What is it? Jack? Y squared x. Okay, because right now, who's the variable and who's the constant? Y is the constant and x is the variable. So what's the integral of 2? 2x. What's the integral of y squared? Y squared x. Okay, so we have to pay attention to who's the variable and who's the constant. Okay, good? All right, now what do I have to do? I need to plug in 0 and 1 here. And I need to be careful. When I'm plugging in 0 and 1, who am I plugging them into? X or y? X, because I just did the integral with respect to x. Okay, so I need to plug in and subtract, right? This is just fundamental theorem. Okay, so what do I get? 1/3 plus y squared. And if I plug in 0, then everything disappears, so I don't have to worry about that. Okay, good? Well, now look what we've got. This is back to basically just a Calc 1 integral. So Cole, for the 360 no scope, what's the integral of y squared this time? Uh-huh. Who's the variable this time? Oh man, I just gave you one. Right?
That does make sense.
I was just sitting there at CT spawn, just sitting there.
I know sometimes when you throw a lob and like it's easy,
Mm-hmm.
you just get nervous.
Yeah.
There was on my sweater.
Okay, so do we buy that the antiderivative here is 1/3 y plus y cubed over 3? Okay, because this time I was doing the integral with respect to y, not x. Yes? Jack, you have a scowl on your face. Okay.
I grind a bike. He's just upset at the world.
Well, I can't help you with that. Because I'm lazy. Right. And it sounds silly because I didn't want to come over here and have to write dy sub naught. Right. So it's just like y is a variable and I can think about, okay, right now it has some value. What value is that? Well, I could call it y naught, or why not just call it y? It's a value or variable. Its value is whatever it is. Okay, this is the fine art of hand waving. Okay, which is proof by intimidation, right? I'm just going to stand over you menacingly until you accept that whatever I'm saying is correct. No, Not a valid proof technique, but okay. All right, so I plug in my numbers here, and what do I get in this case? 1/3 plus. Yeah. No tricks, Kirk. Just 2/3. Yeah? 1/3 plus 1/3? Checks out? Okay. Your task is to do the following. Okay, I did X first and then Y. You guys do Y first and then X. It should give you the same answer. Okay, but go through it and double check that it in fact does. S'il vous plaît. Well, okay, with this particular function, yeah, this is. It's a real good thing it's almost the end of the semester because I am just so done with some of you. Yes, that I won't be teaching. Yeah, I'm gonna. Uh, no, I'm just. Yeah. No, next semester I will be teaching Calc 1, and at the bright, shining hour of 8 a.m., and 2 sections of CS 106 at the bright, shining hours of 8 and 9:45 because I'm a masochist uh, and a sadist, I guess. But yeah, so it's sort of ironic that for being a math PhD, I'm actually teaching more computer science lately than math. But hey, whatever. So yeah, when I'm like, yeah, take linear algebra and take all these other classes, right? Take them with other people. So what? Yeah. Okay, did you guys get 1/3? Yeah,
That should be 2.
or 2/3? Sorry.
We got 1/3, then we're really bad at busy work.
Yeah. Okay. Now, it shouldn't perhaps be too much of a shock that it works out exactly the same way this time because there's a sort of symmetry built into my function, right? X squared plus y squared. X and y are kind of doing the same thing, right?
We're doing exactly the same thing.
Yeah. So, okay, so this perhaps wasn't super enlightening, but if I had made the function something different, we, the details might work out differently from one to the other, but the answer in the end should be the same both directions. Okay. And that's a good thing. Okay. Good. And let me guess, Cole, what'd you get? Bam. Man, would you guys look at Cole? Yeah. Okay. Okay. So great. Now that was maybe too easy in the sense that no, that you could get it right. It was this was maybe a little misleading because since X and Y were playing exactly the same role, it wasn't a shock that it worked out the same both ways. Okay, so let's change the function to something a bit more interesting. Um, how about let's get some trig functions in here. Yep. All right, so let's do, and you know what? Let me change my bounds here because we're going to need, okay, so the function I choose is, for the next one, is we're going to let f of xy be x cosine y plus y sine x. And we'll do 0 to pi in both directions. Okay. All right. So what you guys are going to compute is, okay, so choose one of the two integrals here to do. Choose to do x first, or choose to do y first. So just flip a, well, here, let me just do this. X, y, x, y. Kim, you're doing y first. Jack, x first. Lee, y first. Inside, because you work from the inside out. Okay. Now, we should get the same answer depending either way. Okay. The details along the way will be a little different. Okay. But the final answer in terms of a number should be the same both ways. Well, yeah. I guess my faith in humanity has been both raised and lowered over the last week. So, but it's net been raised. Okay, so we're just taking a breather while you guys work that out. Those of you who are online. Let's see. Looks like we got Farden and Coy. How you guys doing this morning? Sure. Ah, okay. That's fun, right? Because if you look at, say, x cosine y, you might be thinking, oh, I've got to do integration by parts or something like that. But remember, only one of the things is a variable. You're doing y first, right? Y is a variable, x is a constant.
So, but when y is the variable here,
Ah, well, sine x is a constant.
the whole
So,
thing.
yeah.
So then
So what's the integral of 2y?
2y squared over 2.
Okay, so what's the integral of 7y?
7y squared over 2.
So what's the integral of sine xy?
Sine x
Times y squared over 2, because x is a constant, and therefore sine x is a constant. Okay, so like on Friday when we were doing partial derivatives, that ironically, it's sometimes easier when you have more variables because only one of them you're treating as a variable at any given instant. Yeah, and we're going to write out both directions after you guys have a chance to try it. This is called active learning, right? Or at least that's the idea. Right? I mean, because you guys could just sit there and watch me do calculus all day. You know, for the most part, can do it without making any errors. Just do one of them, right? And I'm going to write out both of them. So while you guys are doing that, I'll go ahead and start writing. Um, So, I've got a case of the Mondays. No, that was right. Okay, I've lost a.
You lost the third row up on the left side.
Mm-hmm.
Should be 2y.
Where?
On the left side, the third row up on the left.
Oh, yeah.
Because when you plug in
Yeah.
cosine of x, you get a y at the end.
So that makes this y squared, which makes this pi squared. Okay, good. Okay, so there it is, worked out both directions, right? And assuming you're not incompetent like I am, then you should get the same answer both ways. Now, in this case, though, the details looked a little bit different both directions, right? Because because cosine and sine are different functions, right? But in the end, we end up getting the same answer. Okay. Yes, Donovan. The pi squared over 2. Yes, and the mistake I made was, yeah, right here when I've got y cosine x. Okay, if I plug pi into that, I'm plugging it in for x, right? What's cosine of pi? Okay, so times a -1, I would get plus y. But then I plug in 0. What's cosine of 0? Also 1, and I'm subtracting that thing, so I get 2y, not y. Does that make sense? Yeah, it's just, I think exactly the same mistake I made. Okay. So what's the volume here? Pi squared units, whatever they are. Now, let me be clear about one thing. When I say the volume, what do I mean? Well, okay, if we go back to Calc 1, okay, and I did the integral, right, and we'd say that that was area under a curve, but really what is the area? It's between the curve and the x-axis, yes? And if the function dips below the x-axis, then that area we count how? That stuff counts negative, and anything above the axis counts positive. So in our case, right, what do we have? So I just doctored up the graph to include, in blue, we've got basically the xy plane, okay? What we're finding is the area between, or excuse me, the volume between the surface and the xy plane. But over there at the bottom left, that dips below the xy plane, right? So that portion of it counts negative, and the stuff that's above the xy plane, which is most of it, counts positive. Okay, so does that make sense then? Yeah? Yes, Cole. Mm-hmm. Okay, so that would be here. Okay. Ah, well, I'm plugging pi and 0 in for y, correct? What sign of pi? The Sine of pi halves is 1.
Oh.
Yeah, sine of pi is 0, and so is sine of 0, right? So they just disappear, okay? Yeah, so trig, bro. And I realize we're getting very, very close to the end of the semester. You know what I haven't actually given you guys yet? You remember I've been joking about that punishment quiz? Keep joking? Okay. Right, with your unit circle values? No? Okay. All right, so that's basically what we've done, right? Is area, or excuse me, volume over a rectangular region. Now, as a preview of coming attractions, those of you who go on and take more of this stuff, could we do volumes over non-rectangular regions? Totally. Okay, the formulas get a little bit more complicated, but we could do that, okay? So here, what we've done is basically the Calc 1 equivalent of integrating from a number to a number, okay? Great. And then our interpretation of it is, well, if a single integral we use to describe net area, then a double integral, or two integrals, one after the other, is describing sort of a net volume. Okay, does that kind of make sense? Yeah? Gucci? Yeah? Okay. So, yeah. Now, with both of these examples here, the techniques of integration we needed were all relatively easy, right? And I did that deliberately just for the sake of time in class. But it might be the case that in some problem, we still have to do integration by parts or whatever, okay? Where this gets complicated then is you have to be really clear when you're working it, who's the variable and who's the constant, right? Now, like with the partial derivatives where you can do it in either direction, if I ask you to find the volume or net volume of something and you set it up, which way do you set it up? X first and then Y, or Y first and then X? Does it matter? In theory? No. Okay, assuming the function is nice, which they're always going to be nice for us, right? So if you have the choice of the order, take 10 seconds and think about which order might be easier. Okay, now in this particular example, I don't know which way was easier. Experience. Yeah, I mean, I feel like I'm a broken record because every time you guys ask me that question, I answer the same thing. But I mean, point being, right, you've got a choice, and so it might behoove you to exercise that choice. Okay? Okay. Now, if you guys will indulge me for the last couple of minutes here, let me start to show you something with Mathematica that hopefully will blow your minds. Okay, so let me pick a function. And I'm just going to pick cosine, cosine. Dang it. Dang it. No. Okay, so we get this sort of egg crate looking shape, right? Okay, now let me actually just make it minus pi to pi. We don't need to focus on the whole thing, right? So I get sort of this little part of the egg crate shape. Okay, what would you guys say that we have going on here? I got some peaks, I got some valleys, right? Yeah? Okay, all right. Let me do the contour plot. And actually, let me just copy this. Okay, so if I made the topographical map for this surface, it would look something like that, right? So big shock. What do I have there in the middle? Got my peak, and then I've got the valleys kind of on the edges, and then the more peaks over in the corners, right? Okay, great. And if we were to read this as a topographical map, let's say that I was standing right here and I walked due south. What would happen to my height? Nothing. Okay, that makes sense. I'm walking along a ridge line. Okay, what would happen if I walked southwest from this point? I would be walking up. Okay, and would you guys agree, just looking at this picture, that I would be walking up in the steepest possible way I could? Right? I would be making the steepest climb from that point that I could.
Yeah.
Okay, whereas if I walked kind of like here, right, I'd be going up, but I'd be doing so more gently than if I just went straight up the mountain. Okay. Now, what is the gradient of this function? Well, what's the gradient defined as? It's the partial with respect to x, comma, the partial with respect to y. What is the partial with respect to x of my function cos x cos y? Okay, that's the partial with respect to x. What's the partial with respect to y? Okay, and I put this in curly braces because this is a vector quantity. Okay, now the gradient, if I pick a point, I could plug in its x and y coordinates to that function, and I would get a vector, right? Because it's got two coordinates. So what I'm going to do is I'm going to think of, all right, at every point on the xy plane, take the coordinates and plug them into your gradient. You get a vector, and then draw that vector at that point, okay? So what this is going to be called is a vector plot, and I'll actually change this. Um, okay, so here what I've done is at every point in the plane, I've taken its x and y coordinates and plugged it into my gradient function. And then that gives me an arrow, a little vector, and I'm going to glue that vector at that point. Okay, interesting looking stuff we got there, right? Okay, now what I'm going to do is layer these on top of each other. Oh, and I want to go the other way. I want to do P2 comma P1. Okay, all right, so what do we notice here?
They're all pointing towards the. Well, they're all pointing away from the.
Yeah, they're pointing away from the valleys and straight towards the peaks, sort of. Okay, I haven't really picked the best function to demonstrate this. I'll show you guys another one maybe next time. But in particular, there's two things I want to notice. If I'm at, say, let me pick a point with my mouse cursor. If I pick a point right here, say where my mouse cursor is, which direction do I need to head in order to be going upwards at the steepest possible? I need to go southwest, which is exactly the direction the arrow points. But if the point I'm at is, say, over here, which way do I need to go upwards as steep as possible? Well, it's not southwest anymore. It's sort of west southwest. Uh huh. Well, No, but it's which direction do I need to go upwards as fast as possible?
Oh,
Okay, which would mean to go directly away from the valley. Okay. Okay. The other thing to notice is that you see my contour lines, which are level curves, right? Level curves in Z. What's true about the arrows and the contours? Okay, so like where my mouse cursor is, there's a little orange arrow, and there's also that black contour. What's true there? Uh, right, yeah. So I got this arrow, and I got this contour line. What's true about those things? They are. Okay, so if you are at a particular point, the contour that goes through that point and the gradient vector at that point are always perpendicular to each other.
that makes sense.
Does kind of make sense, right? Yeah. Okay. Well, we should quit because Pofald's getting antsy. So,
What's happening on the four corners?
huh?
What's happening on the four corners?
They're peaks, but I just haven't graphed more of it.
What, no, sorry, the four corners of the square there in the middle.
Here? Oh, a saddle point.
Uh,
It's like a three-dimensional version of a point of inflection.